Let's talk a little bit about impulse and how impulse relates to momentum. What we've been talking about so far are collisions, where we have two things colliding and maybe sticking together, or two things colliding and bouncing. And our main way of tackling those problems was by using conservation of momentum. But oftentimes, what we want to do instead of colliding something together is we want to speed something up or slow something down. And the concept related to momentum, and that is impulse. So let's just take a quick example of a car crash. So let's say we've got a wall over here, and we're going to crash this car against the wall, just like that. Now, it turns out momentum is still conserved, but the system for momentum to be conserved is the car and the wall is attached to the earth. So it's hard to notice the change in momentum of the earth. So we usually don't do problems like that. But what we can do is we can notice that the momentum of the car actually changes as it hits the wall. It gets slowed down. And so we can talk a little bit about airbags as well. Let's just draw the car up here like this. There's our car. And just to make the numbers really easy, let's say the car has a mass of 100 kilograms, and let's say it's going at 5 meters per second. And then the car is going to crash into the wall right here, crash and stop. And when it stops, obviously, it's going to have a speed of 0 meters per second. So you can see the momentum of the car did actually change. And where did it go? When we say that momentum cannot be created or destroyed, the momentum of the car went into the wall. So you can think of a collision between the car and the wall, which is attached to the earth. The earth went a little bit faster after the car got colliding. Mass-wise, if you think about our formula here for final velocity was m1 v1I divided by m1 plus m2. If you think about the earth as the mass for m2, since that's what it collided against and stuck to, you can see that this denominator is going to be pretty small right here. And then the final velocity of the car and the wall together. Remember, this VF here stands for the final velocity of the two things stuck together. That's going to be a pretty small number, right? If you consider the mass of the Earth is 6 times 10 to the 24th kilograms, that's going to be a small number right there. So essentially, it's 0. But what we can keep track of here is we can say that the car had a change in momentum. We can keep track of that the car had a change in momentum. And how much did its momentum change? So we'll just do that as delta P. And remember that P equals mv is our formula for momentum. So this one can actually be thought of as final momentum minus initial momentum. The final momentum here is going to be 0 because it stopped. And then the initial momentum is going to be its mass times velocity. So we had 100 kilograms times 5 meters per second. So the change in momentum was negative 500 kilograms times meters per second. Good. So what do we want to do with that? We want to relate that to how the car crashes against the wall. And if you've ever been a passenger in a car and you've been in a crash, I hope you haven't, but we put some safety features inside of cars in order to help the people in the car not get too hurt when they crash. One of them is an airbag. So if you have an airbag and you're driving along and you stop, your face is going to hit the airbag. So what does an airbag do? Well, as we saw in class, one other way to talk about change in momentum is to say that it's actually impulse. Impulse up here is change in momentum. And let me get an eraser. So change in momentum for impulse was actually force times time. And if you're going to have a collision with the wall, then you've got to have a force and a time in order to change your momentum. So in order to get this negative 500 kilograms times meters per second of change in momentum, you have to have a force times time. Just to review again the units right here, force units are meters per second squared, kilograms times meters per second squared, and time units are seconds. So units-wise, this still works out to kilograms times meters per second. So it's still momentum units. Getting back to the airbag thing, you've got a little bit of a choice here. If you're going to change your momentum, you can have a big force over a short amount of time, or you can have a smaller force over a bigger amount of time, or you can have it sort of be medium. And the idea behind an airbag is that if you're going to crash into a wall and your body is also something that's going to need its momentum to change, then you've got a choice. You could slam straight into the wall, maybe you could hit your head against the windshield, something like that. That's going to be a very big force over a short amount of time. Or if you expand the time out, then you can reduce the force. And we saw in class, we had some graphs here of force versus time. If you have a very big force in a short time, you might see a really big spike in your force. That's not going to feel so good. What might feel better is that if you expanded the force out over time, then you can have less force. Less force and more time, and you're still going to have the same impulse. As far as the car goes, it needs this much impulse in order to stop. It needs 500 kilogram meters per second of impulse in order to stop. Well, you can get that from, say, a really big spike in the force over a very short amount of time, or you can get a smaller force over a bigger amount of time. Because we're not really going to be doing calculus in here, it's going to be better if these end up being rectangles, because then we can find some areas. So let's make this big spike right there, and then that's for the non-airbag. And then if you have an airbag, let's stretch it out over time just like that. And for this, just throw some numbers on here. Let's say that the very fast impact where you slammed into the wall happened in, 0.5 seconds. So you can see that the amount of force we can have here, we can calculate the amount of force. We've got 0.5 seconds, so all of this has to multiply out to be negative 500. So what we're trying to do with the car is we're trying to get 500 kilogram meters per second of impulse. If I have that as force times time, my time here is 0.5 seconds, force times 0.5 seconds. You can see that that's going to mean that my force is going to need to be, I'm dropping things here, my force is going to need to be 1,000 newtons. If I instead have this force over here, and let's say that that is spread out over, a span of, say, 2 seconds right here, and if I redo this equation over here, and I say 500 kilogram meters per second equals my force times 2 seconds, then down here you can see that my force is actually only going to be 250 newtons. So if I stretch out, there's my 1,000 newtons. If I stretch out my time, then I can decrease my force. And that's what we like to do with impulse. And the last thing to remind you about is that this is actually the area under the graph right here. So the area underneath this graph is going to be 500 kilograms meters per second. The area under this part of the graph right there is still going to be 500 kilogram meters per second. So we need to keep those areas the same. Just to make a little note right here, area is going to be your impulse. Okay, great. Hopefully that helps you out.